Unbox Your Phone, Exploring and Working Samsung TrustZone Sandboxes, Daniel Komaromy. El sistema de Sandboxing KNOX de Samsung apunta fuertemente a la seguridad, pero Daniel Komaromy nos trae un profundo análisis en donde investigó a fondo las TrustZone OS y los mecanismos IPC usados para cruzar los límites de Sandbox. Esta investigación llevó a más de una docena de nuevas vulnerabilidades que efectuaron todas las versiones del T-Base de Samsung, incluido en el Galaxy S8. Daniel Komaromy es investigador de seguridad móvil y un ávido jugador de CTF con Spam and Hex. Habiendo ganado títulos de MSC, de BME y Georgia Tech, tiene 10 años de experiencia en el campo de la seguridad, trabajando en ambos lados de la cerca como un ingeniero de seguridad en Qualcomm y luego como consultor de seguridad en una firma boutique.
Hey everyone, welcome to Unbox Your Phone. I'm Daniel Komaromy. I have no idea what the announcer just said, but I hope it was all great stuff. So let's get started. So today I'm going to talk about TrustZone reverse engineering and vulnerability research. And the first question, I guess, is why? Many aspects of TrustZone research has certainly been exhaustively researched already in the past, but mostly on other targets. So other vendors, including Huawei, but mostly Qualcomm, has had a lot of attention paid to the TrustZone implementations. Tons of vulnerabilities have been found and exploited, but pretty much all of that work was done with just static reverse engineering, and obviously with all the respect to the researchers, most of the times it turned out to be pretty straightforward exploitation, thanks to the fact that those TrustZone implementations pretty much really failed to meet their lofty goals and are neither small nor compact and have basically terrible isolation properties, so we're really soft targets. On the other hand, the Samsung's TrustZone implementation to date has pretty much remained a big black box. So very minimal research has been done on it, at least publicly. This year, Project Zero published some stuff on trustlets, but the entire operating system itself has still pretty much remained a mystery. So my main interest was in exploring the system itself. So given that, this talk is mostly going to be about reverse engineering with a little bit of vulnerability stuff for good measure as well. So to get started, let's just get out of the way all the things that we already knew about the TrustZone implementation that Samsung uses. First of all, what does Samsung use TrustZone for? Well, this is actually really extensively documented. So the what of it is very clear. Actually, Samsung does a great job at. They have their own KNOX website that you can go read it, and there's really tons of information on what are all the things they use it for, what are the different features. However, it pretty much doesn't say anything about but how is this implemented? On the other hand, it's known that the operating system that they use for the TrustZone actually comes from a third party, and this is the first thing that made it interesting for me because the likes of Qualcomm and MediaTek and Huawei, they all make their own TrustZone. Obviously, they are not a company specifically focused on implementing trusted execution environments, and honestly, it sort of shows. But in the case of TrustZone, this is a company that this is the only thing they do. This is literally their entire business model, that they make these trusted execution environments and they ship them into all kinds of things. Of course, my focus was the Samsung's mobile phones, but this shows up in, according to their marketing data, whatever, 500 million devices or something like this. And actually, this is a really long history. It's actually the third name of the company already. So this implementation, you could say, is pretty mature. It's been around for something like 15 years. And it has certainly been done from the ground up with the goal to actually create a minimal environment, so truly a microkernel. So, the things that we know about it that I'm really not going to talk too much about because it's, I guess, public info. First of all, the protocol that is used to manage interaction with with the TrustZone OS, which is called the Mobile Core Control Protocol. And then it's known that TrustZone themselves ship a bunch of Android components to make integration easier. And all of this is, or a lot of it is open source. So exporting that part is pretty easy. And also, quite a bit is known about the formats of the trusted applications themselves. So they have a proprietary file format, but this is also documented in open source code. And then, it, of course, being a different operating system, has its own libc, which they usually call mclib or tlib. It's one of those things with TrustZone, like everything has 15 names, so it's a little confusing, but we're just going to call it libc. So the calls in this are somewhat researched, so some of it are known, some of it not known. One important part is that even though they provide a bunch of Android stuff like I mentioned, at the end of the day, the integration ends at one client library that then any vendor can, okay, if you want to actually use TrustZone, you would presumably put this into your applications. And so that was one of the things that I was really interested in seeing, okay, how does Samsung actually integrate this, meaning what interfaces are we going to end up with if you're an unprivileged Android process. Obviously, it's pretty clear that if you assume something like I can write a kernel driver or I'm root, then obviously you can talk to all the aspects of TrustZone. But what I was more interested in seeing is, okay, what can we do if we start from zero? So a quick word about, why is this kernel actually a microkernel? So if I, again, not to beat a dead horse, but if I again look at the Qualcomm example, then what you saw there is, well, if you start looking at, okay, what kind of SMC call handlers exist, there's dozens, even hundreds of them. So it's a gigantic bloated kernel. In the case of TrustZone, the ones that really matter, there's pretty much two SMC calls. That's it. One is an initialization call that is used to set up basically Android telling the TrustZone where is an area of physical memory that will be used to share comments through, so basically comment queues. And then there's a single other SMC which is just used to tell TrustZone, hey, there's another comment, go look at it. And that's it. That's all there is. And everything else is through shared memory, so that's how this MCP is implemented. And so the Android and the TrustZone pass comments through this shared buffer to do things like initiate, basically loading a new trustlet, or to then share, again, memory with the trustlet. And then if you want to talk to a trustlet, a trusted application, then again, through the specific shared memory, you just pass data back and forth. So what follows from that is the kernel is going to be really, really minimalistic. It pretty much, you would expect that it's going to implement those two SMCs. It's going to implement some process scheduling and whatever system calls are necessary, and then everything else should be in processes. So we knew all that. And then here starts the things that we didn't know. So first of all, okay, where is all this firmware? What is the format? How can we find it and look at it? What does the startup and basically these baseline features of the microkernel look like? So how do processes get managed? How is the MMU configured? Things like that. Like I mentioned, what are the system calls? As any other operating system, of course, this is going to have system calls. And again, it's a completely proprietary thing. So we don't start out by knowing, okay, this one is read, this one is open. We don't know anything. And then, of course, there are questions like, okay, well, we know that the MCP comments are documented, but how is all this actually implemented? Or similarly, we know from the documentation these two SMC calls, but is that really all there is? Or maybe, does Samsung add more and so on? And then talking about trustlets, like I mentioned, there's like a generic understanding of how they work, but there's details about how they're getting loaded that's unclear. For example, how does this libc get loaded into trustlets, address spaces. A thing that when I started out was unclear completely is, okay, which trustlet actually implements what? Like I mentioned, if you go on Samsung's website, you find, gazillion amount of data on, okay, there's a secure key manager, there's secure certificate management, there's kernel monitoring, there's this and that. But there's nothing that maps this to, well, this is that file, this is that file, this is that file. Another thing is, okay, what is the difference between trustlets and drivers? This is not really spelled out very clearly in public documents, but there are different types of processes in this operating system as well. Basically, processes that run with different privileges. And presumably, the drivers are going to be more powerful. But what exactly does that mean? Are they as powerful as the kernel itself, like in the case of Linux, I guess, or is it something in between? So this is unclear. And then, of course, how are all these libc API calls actually implemented? And associated with that, what isolation do we actually end up with? If you remember, when I started out, what I was saying was, well, on these other, more naive TrustZone implementations, the isolation is pretty ridiculous, but here it's supposed to be better. So that was one of the things I was interested in, is it really better? And then finally, briefly, as I mentioned, all we know going in is, well, there's a shared library, and if you want to do something on Android, you can load it. But, okay, what actually happens, on my phone? What applications really use this, and how is it restricted or not restricted, etc. So for the first part, I'm going to talk about starting out with pretty much a black box with some assumptions and pretty much thoroughly reversing the entire microkernel. So first of all, we have to figure out where all the firmware is. It's interesting. Recently, there have been some things published on this, and so people talk about, okay, you can do some bin walk magic to find this and find that. But really, it's actually super simple. This is the only part that was really, really simple. Because if you look at the sboot binary, which normally you would think, well, that's where the application bootloader is, in it, there's the string tbase, that's the name of this operating system, so it's a pretty dead giveaway. And then starting there's this great header table, which basically tells you the offset and the size of all these firmware components. So right off the gate, this part was really easy. So, okay, we know, okay, this is the microkernel firmware. These are a couple of drivers that are for some reason embedded in the firmware instead of being on the file system. It becomes clear later why that is. One of the things that are embedded in here is the libc that I talked about. And then there's one more thing, which at first I had no idea what it is. And I still, to this day, have no idea why it's called this. But for some reason, its name is S0CB. Sorry, but I have zero idea why it's called that. Just so you have the context, I'll explain this. But what this ends up being, what this turns out being, is pretty much the equivalent of a DOM0 in hypervisor world. So like I mentioned, really, this is going to end up being a very small microkernel. So really, all the operation actually also happens in a process, in user space. And that's what this S0CB is. It's basically this special privileged process that handles all the things that I guess you would say that in other TrustZone implementations, they all actually still push into the kernel. Now, if we want to get a complete picture, it's important to see that this TrustZone really only implements the secure world. And so on ARM, if you have the secure world and the non-secure world, you need to have this glue between, which is called the monitor mode. We could fill an entire presentation just with that, but luckily, recently, Fernando from Quark's Lab, well, he was there at the time anyway, did an awesome blog post on this explaining all the ATF aspects of this. So go read that. Really, anything you ever wanted to know about how the monitor mode is done here is explained there. So we skip this entirely, and we are just going to assume that the secure world and the non-secure world really directly talk to each other through SMCs. And so with that, we can start looking at the actual firmware. And so at first, obviously, I started from the most obvious point, the entry point, to see what happens. You have to figure out the loading address in IDA if you want to get things right. This is pretty straightforward for a number of reasons. By now, it's also been documented online, but the biggest reason is that it's trivial to find on Google logs of device boots where you can see that this is the case. Something that helps here is, I'm focusing on Samsung, but there are other vendors, Xiaomi, Huawei, MediaTek, HTC, that also use this TrustZone operating system. Obviously on different devices with varying degrees of debug enablement. And on some of them, it's trivial to get startup logs out of the devices, so that's how this was pretty straightforward. But beyond that, the whole thing is just you know, if you're familiar with Samsung reverse engineering, then when I started looking at this, it's very disappointing. What I'm talking about is Samsung loves strings. If you've ever, you know, looked at anything that comes from them, everything is full of debug strings. You can always pretty much find the name of everything. Basically, a non-symbolicated Samsung binary is actually really a symbolicated Samsung binary most of the time. However, this, unfortunately, the kernel, of course, is not written by Samsung. It's written by TrustZone. In fact, from all I understand, the vendors don't even get the source code for this. So they can't even change it. And really, there's basically literally 0 strings in here. So that's not so great. But we still have something to go by. Typically, in this kind of low-level code, what helps is, of course, although the whole thing is proprietary, it's still based on ARM. It's still based on a known context architecture where we know what certain MCR instructions do. So we can find where is the place where they set the VBAR, which will tell us where is the syscall handler, where is the SMC handler. We can find where the MMU or the caches or whatever get enabled. From there, we can see what is the address that is set to the TTBR0, which is the page table that the kernel uses, and so on. So you get little hints, and of course, as you would imagine, the beginning of the startup code is all, you know, there's nothing in there that looks like this will be related to TrustZone, right? It's just really the basic stuff, like I mentioned, setting up an MMU and things like this. But then comes the part which actually becomes TrustZone specific, and here what helped was pretty much the intuition that I knew what I had to be looking for. Meaning, at first I was just looking around the code, and it became pretty clear that if I look at all the startup sequence that at some point adds in trapping back to the monitor mode, that, well, none of this does anything related to these MCP protocols. And if I looked at the handlers that it can later invoke, like the SMC handlers, none of that does anything related to that either. So that made it clear that, well, that has to be somewhere else. And so that's where I had the intuition that, okay, all the code in between, which at first I don't know what it is, what it has to be is the creation of a process, which is going to be this DOM0 process. And that was the point where it also became clear why they actually embed some of the drivers into the firmware. The reason for that, of course, is that since this is also a process, the DOM0, it needs the crypto driver to actually do like cryptographic verification of when it loads trustlets. But of course, until the crypto driver is loaded, it cannot use the crypto driver to do cryptographic verification of anything. So that's why in the actual DOM0 code, there's 2 code paths, one for loading trustlets when you actually verify them, and one for just loading them blindly. And it only uses the second one, luckily, in its startup sequence. Obviously, that's when it loads the kernel driver, which was, by the way, really helpful, for example, for understanding how trustlets are loaded, because there was one code path which was all the crypto and all the loading, so it's more code and harder to figure out what's what. But then there was another code path which is very nice, very cleanly, 0 sanity checking, 0 verification, just plain the minimum amount needed to load the process, which obviously made it easier to isolate things. But I'm getting ahead of myself, because before we talk about the DOM0, a couple more notes on the kernel itself. So like I said, okay, we can figure out, okay, this is more or less the code where it loads the process. But from the VBAR setting, we can find where the SMC handler is. And so that's nice, because as you can see on the screenshot, I'm not sure how visible it is. Once you have the SMC handler, that is fairly straightforward to identify and match it to the known published SMC codes that I talked about, like the notification and the init and so on. There's a couple more, but it's really irrelevant for us. However, something that was very interesting is that I look at a simple switch case, and some of them, well, all except for one, matches what you expect. And there was one more thing, and lo and behold, of course, there's a feature to actually implement custom SMC fast calls. And if I would have to guess, TrustZone does this so that, since vendors get all this as a binary, so that vendors have the ability to add fast calls if they really want to. So at that point, that was something I was interested in, whether Samsung does that. There's no points for guessing right that, of course, they do, and they added a bunch. But I'll talk about that later. So we have these, and now there was that remaining little bit of code of, okay, I look at it and I have no idea what it is, but I know that what it's supposed to be is loading a process. Well, if you're going to load a process, then you will need to be doing one thing for sure. You will need to be modifying page table entries. So you will need to modify the page table. And so that was pretty much the one thing that was helpful in sort of putting the bits and pieces together. And then the other part of it was that, of course, as I mentioned from the beginning, both the library and this DOM0 is straight up embedded in the flatly loaded image. And so there's like a known address where this is at with a known header format. So if I start looking at this remaining mumbo-jumbo code, I can look for the references that will start reading from there, and that will tell me, okay, well, this is the point where it grabs it, and follow from there to see where it's going to load it, and so on. And so that all sounds good, but what really happened for me for a long time is, okay, this does some syscall, I don't know what any of this is, something, magically load process. And that was what function names first looked like in my idea. It was like magic something load process. I don't know why, starts process, things like this. And then what essentially helped me after a while is, well, something that was very useful is that there is zero dynamic memory management in the kernel. This is great. So there's no heap. And so that means that everything is at static addresses. So all the different things that turn out to be process descriptors and things like this, page tables for various processes, everything is maintained at fixed addresses. And so that means that, of course, if you can find the one function that initializes and resets a structure, and then you know its address, then you can find all the cross-references that will also touch it, because we're just passing stuff around with pointers that point to nowhere. A heap, not nowhere. So that was the one thing. And the other thing that was useful is that at the end of the day, you expect that at the core of all this, everything boils down to what's implemented through syscalls. So you would expect that there has to be a syscall, for example, for starting a process. There has to be a syscall for starting a thread. There has to be a syscall for some equivalent of an mmap, and so on. And then so what I started doing was try to match the different parts that should be doing similar code and use that to figure out what syscall is what. So here, there's two examples on the slide. In the DOM0, like I mentioned, there's code to start processes because, one of the MCP commands is opening sessions. But also in the original kernel sequence, like I mentioned, there is the code to start processes, since, of course, it starts the DOM0. And so by matching, okay, what this does here and what this does here, where does it overlap, that's what helps identify, this is the syscall that I'm guessing actually starts a process, and if I look at the implementation of the syscall, then incredibly, the function that I find it using is the same thing that was used in the kernel startup process. So, all right, that's creating processes for some reason. Then all that this does is it touches some kind of descriptors. Then these are going to be process descriptors somehow. And then it sort of goes like that. The same thing for mapping. So we know that there is MCP commands for mapping memory, but there's also libc commands for mapping memory. And so if I look at what the implementation of each are, then again that gives me a hint for these two are using the syscall, nothing else uses that syscall, but that's going to be the mmap somehow then. And so on and so forth. And then, lastly, honestly, this is all nice, but really something that of course helped a ton is, even though the kernel has just no strings at all, and the same thing for this DOM0, pretty much no strings, there's tons of strings and debug strings that identify functions and command types and stuff like that in the trustlets that were written by Samsung, which is very nice because this was what helped to identify the names of the libc calls and the semantic meaning of the libc calls that weren't clear. And from there, look at the internals of the libc calls and then start matching them. For example, okay, I find the libc call and I would have no idea what on earth it is, except the Samsung trustlet nicely tells me that this is a libc call for starting a thread. And then I look at that libc call, and all that it does is it makes a system call with the comments just proxied. So, okay, now I know what that system call is, and so on. Here's some examples, but this is more there so that it's useful, offline. For example, here you can see that at the end of the day, there's I think like 30 or so system calls. In the end, I was able to figure out every single one of them except for 2, which I couldn't find anything that uses any of those syscalls, not a single trustlet or anything. So I don't know what they are, but they didn't seem particularly useful for me. And so a couple words also about the DOM0 itself. So far, of course, I've talked at length about the fact that this is where all this MCP handling is implemented. And that's very convenient to work with, because again, I look at the code, and even though there's no strings, I know what the input is like. I know what kind of comments it will implement. So when I find its big switch case with the IDs matching exactly the known IDs, obviously you clearly know what's what. And you know the comment formats, because remember, the other part of this communication is in the Android kernel, all open source. So that's very nice. And that was one of its threads. And then it had 2 other threads. And so that was the stuff to figure out. One of them was pretty straightforward. So here's an example. You can see this part is pretty easy, matching like, okay, that's that comment, that comment, that comment. And then you can straight away start looking at, okay, how trustlets are loaded and so on. Let me do this the other way around. Whoops. Why did I just push? Oh, interesting. Let me, 1 second, you guys. Okay, yeah. So, yes. Like I mentioned, it has 3 threads. One is for the MCP handling. The second, if you recall, one of the things that has to be implemented by TrustZone is to handle these notification messages from the Android. So that's done in here as well. This was fairly straightforward to identify after I was able to know what syscall does what. Because if you see in here, well, it's easy when I mentioned it, it's called init MCP queues and things like this. But really what happens is that there's a syscall, which is a control syscall, which you can use to get back from the DBase kernel the addresses of these different queues. And so you see it's a big loop. It starts with getting those addresses and then mapping those into its own address space, and then it loops forever on reading into them, and when it sees new information, then using the syscall, which is the notify the trustlet or send a signal to trustlet syscall. So that's pretty straightforward. The other thing that was a lot less straightforward is the 3rd thread, which turned out to be the IPC implementation. So, what's the time? So, at first I had no idea what this was. So even for the IPC syscall, in the syscall table, I was like, okay, this is a whatever. And this whole thread, at first I didn't really think about what this is at all. And so I put this to the side, and I was looking at trustlets and figuring out what they do. And after I've been able to figure out sufficiently enough libc calls semantically. So if I would look at all the things in libc, I pretty much knew for all the calls, almost all of them, this is what this is, this is what this is. And I started looking at them, and then I couldn't help but notice that some of them map to specific syscalls, but a really, really big amount of syscalls, specifically all the ones that intuitively look like that this is a syscall, this is a trustlet API call, which basically means I want to go talk to another person. So call driver, also all the crypto calls, which you can figure out that, well, those are technically separate calls, but really they're also just a way to call a driver, in this case the crypto driver, and so on and so forth. All these map to this one syscall, and looking at the arguments that are marshaled to it when it makes the syscall, after a while I realized that those specifically match the big switch cases that this thing here has. And then after a while I realized that basically this is the handling for all the IPC, and the handling of the IPC call in the kernel itself, although at first it looked like a big mess, in the end it really is again very, very minimal. Really all that does is that when a trustlet or a driver makes an IPC calls, that finds its way into this thread, and it takes the argument that identifies the comment to figure out what the trustlet or the driver is asking to do. And this can be mapping memory, which is important because that's how trustlets and drivers talk to each other, that they map each other's address spaces. It's kind of the same primitive that you see between the secure world and non-secure world. So you can map memory, or you can make IPC calls where you don't pass anything in memory, it just gets marshaled and then goes through register values and so forth. There's quite a lot of them. Here you can find some examples. Altogether, there were something like 40 IPC calls. I was able to figure out what 30 of them are. Again, for me, that was sufficiently enough that I could see how things work, but there's certainly work to be done there. In terms of enumerating all this properly, so the sys calls and the MCP calls and the IPC calls and the formats of all these things, obviously the talk would be even longer and even a lot more boring than this if I went through all of that. So this is more just to give you an idea, and after the talk I'll be putting this stuff up on my website so that it's there sort of as a knowledge base. So we talked about this, and with that, now we have a pretty good understanding of what's under the hood. Something that I actually didn't talk about, so let me mention real quickly is, of course, in all of this, there was this suggestion that, this implementation is not going to suck, meaning there's going to be some proper isolation between the trustlets or the drivers and then the microkernel. The whole hope was that if you get one buffer overflow in some trustlet, it doesn't mean that everything just cascades away and you're all done, like in the case of some others. I think enough of bashing other vendors. And so I guess as a researcher, you kind of want to win, but still I was happy to find that, in fact, once I started to understand, okay, what each sys call is and what each MCP call is and what each IPC call is, this part was done properly by TrustZone. So for the calls that would be dangerous to be allowed to a trustlet and should only be allowed to a driver and all these things that you can think of, there's always checks that look at the type of the context of the caller, so whether it's a trustlet or whether it's a driver. There's basically three kinds. There's trustlet, and there's system trustlet, which is like a privileged thing, and I'm simplifying, but that's what the DOM0 is. And then there's the drivers. And the TLDR is the drivers can do anything. They are all powerful. They can map any memory. So whereas trustlets are really very nicely confined to their own space. So normally trustlets can't do anything, pretty much, apart from, of course, they can talk to drivers and they can issue syscalls to the kernel. So, it becomes a question of, okay, can you find bugs in a kernel or can you find bugs in a driver implementation to actually break out of a TrustZone or of a trustlet sandbox? Because by itself, as it turns out, from understanding what are the APIs that are there for a trustlet, if you're executing code in a trustlet, it's great, and you get a CV and whatever, but by itself, it's typically not very useful, even though it really depends on a trustlet. And at the end, when I'll talk about some vulnerability examples, you will see that sometimes you don't even need any memory corruption to do something really nice. So this is what I was just talking about. In the interest of time, let's skip through this and just let me mention briefly that, as I said, the main thing with the trustlets and the drivers was to figure out a way to efficiently basically re-symbolicate the binary, which is to say, if you see a driver, then we know that there's a lot of trustlet API calls, like these TL API calls and DR API calls. But by default, if I look at a binary, even though I keep talking about a libc, things are very different from when you have like an SO and things like this. There's no import and export tables that will specifically tell us, okay, well, this guy is calling this function by name. Instead of that, everything is only by numbers, and the global offset table approach that is being used is pretty straightforward. For every libc call that that is compiled into a trustlet, that just turns into a simple stub that takes the fixed, always same address of the of the entry point of the libc, and then puts an ID which identifies the call you want to make into the first argument, and then just jumps there. And everything else is being done by the library itself. Which is to say, just by looking at the trustlet, there's no way to figure out, just by the code, I guess. Okay, well, it's a library call, but is this, hashing, or is this forking, or what does this call do? And so I guess that's where, obviously, Samsung to the rescue, and the bucket ton of strings in the trustlets helped a lot with figuring this out. And from there, I wrote a script that can symbolify trustlets and drivers automatically. So again, at the end of the day, this is the complete listing of all the trustlet APIs and driver APIs that I was able to identify. I don't know how many of them there are, something like 150 or whatever. Something that's interesting about this, I really have to mention that I said that, there's good prior art on this, and a bunch of these have been known. Like Tim Newsham wrote a blog post about exactly this, I don't know, something like 5 years ago. But of course, something that happened in practice is that, TrustZone is not just sitting there doing nothing. Unfortunately, they keep apparently adding new APIs. So, for example, when I looked at example trustlets from like Samsung Galaxy S5, and I could see that, I look at this and I look at the trustlet API names that were already known, and that's all it uses, great. When I looked at something newer, then what I saw was, I know these, but it's not using any of those. It's using all new things now. But alas, thanks to all the strings, I was able to match up most of them. And then here, this is just to give you an idea. There was all these, and then all these, and then all these, and then all these, and that was just my 2 phones. So once you start looking at, what are the trustlets on this device, and that's the default device. So not before you turn on any special KNOX feature, before you download Samsung Pay, any of these things, already you end up with a ton of these. And so at that point I said, I'm not going to go ahead and just reverse engineer or, by randomly picking or whatever, because there's too many of them. So we need a better way. So I figured I want to do 2 things. First of all, I want to figure out how can I see which one is interesting in the sense that it actually would be running in a way that's accessible from an unprivileged context. And secondly, I wanted to create some kind of ability to do this dynamically and not just statically look at things. It's nice that I know the names of the syscalls and the libc calls and that I can have a little idle script that maps them. But first of all, there's a lot. And the other thing is, honestly, it just gets boring, right? And so I started looking at the Android part. First thing that I looked for, and this is the part where you just I'm sure everybody had done this, where extremely sophisticated, just randomly looking around on a file system looking for things that having the name TZ or T or TIMA or Secure or whatever. From this, of course, in sysfs and procfs, I've found a bunch of file system nodes that give some debug info. In the end, the thing that was really useful is the last one, which for some reason gives the total log of all the things that trustlets and drivers log away to unprivileged, Android user. Which is lovely. When I first saw this, I figured, great, this is going to be so much easier to work with. Eventually, this also turned into a gigantic security hole, as you will see in the end. Well, that's, incredibly surprising. And then the other part was literally this. This is where you feel like, I'm definitely a security researcher now because I'm string grabbing from, secure. But yeah, if you start doing this, you will very quickly see the Samsung way. Everything goes through everything, through everything, through everything. What I initially thought was hey, I know, libmc client.so. I just have to look at who loads it, and then that's where I will see the actual code. No, right? That's not what happens. This library calls that library, calls that library. So this was extremely boring and annoying. But the bottom line was that after a while, I was able to figure out that there's one process that was particularly interesting to me called TLC server, where the TLC part, of course, stands for Trustlet Connector, which sounds like that this really should be the thing that stands between the rest of Android and actually talking to trustlets. And as it turns out, what this does is it can load several different trustlets, and then it exposes access to those trustlets via binder. So, yes. the interesting thing was, okay, all right, so there's binary calls on the system, which you can directly use to open a trustlet and talk to that trustlet. Well, it can't be that easy, you would think, because that would be terrible. And in fact, the way this is implemented is that there's the open command, and then there's the communicate command. And the communicate command in the binary handler, it basically uses SE Android policies to decide whether it allows or disallows a binary call, which is fine. However, there was also the communicate via shared memory command, which had zero authentication. When I first saw that, you know, your immediate thought is that you're not some kind of like super hacker, but this is probably a deprecated feature that they left in here. And that turned out to be the case. So Samsung was nice enough to tell me after I reported this and they fixed it that that's exactly what happened. And it reminded me of all the reasons why I not work at a vendor anymore. Because it was very interesting to hear from the guy who did the disclosure process tell me that, we found this a year ago actually, and I remember telling the team to fix it, and good thing you reported it because we totally forgot about it. So our gain, and so what we ended up with is, this is actually pretty powerful. So just to be clear, where we landed is there are few trustlets that we can talk to with zero Android privileges. So now, of course, you would have to find some bugs in them, but that's a pretty decent start. And so at this point, like I mentioned, I don't know, I was more interested in sort of putting together some dynamic capabilities than really the bug hunting. Nonetheless, since we really don't have that much time, it looks like, even though, can I get an idea for how much time I have left? Oh, 5 minutes? Oh, so the fact that we started 5 minutes later doesn't count. Okay, great. Well, in that case, I think we don't have much time to talk about this, so I'm going to skip this and talk about the vulnerabilities instead, because I guess we're at a security conference. So altogether, even though I really didn't look at that many things, because like I said, I just restricted myself to the ones that I could access, so that's in practice two trustlets. One of them is the client certificate manager, and the other one is the ESC communication trustlet. But nonetheless, and then of course all the things that sit behind them, which is to say the secure drivers that they talk to. Nonetheless, I was able to find quite a lot of bugs in here, all kinds, some memory corruption, some logic bugs, both in the trustlets and good enough bugs that would allow full code execution in the trustlets, and then from there, bugs in drivers, particularly the TEMA driver, which is used by both of these guys, which then would allow code execution there, and then obviously then you can do whatever you want. So now I'm just going to show a couple examples. This first one is to show that TrustZone can go ahead and develop a microkernel for 15 years and do all this stuff and all of that. But at the end of the day, you can end up with this situation. So this is a trustlet which is meant to be a communication to the super secure Overture, ESC, smart card, NFC enabled, oh my God, Samsung Pay is so secure thingy. And so at first when I looked at it, okay, I don't know anything about any of this, but you can identify the ISO standard that describes how you talk to smart cards, and then under the hood that uses SPY, and then there would be a bunch of like, okay, this is just random memory map, the IO, I don't know what that is, but luckily in the old days, this was all done directly in the Linux kernel before TrustZone, so there's an open source kernel driver implementation of the same exact thing, so that tells you clearly, okay, if you write to that address or this map registered, this is this. So at the end of the day, it becomes pretty clear what happens, so it's easy to look at the comments, and then you end up with code like this. So, okay, here's a comment. On its stack, it has this like simple stack-based stack buffer, and this is a comment used for installing a root cert, right? So the whole point of this ESC communication is that it's supposed to give you a way to create this secure channel. So you can give it a certificate, and based on that, you can encrypt your communication. And so the very, very first thing you need to do is you have to install a cert. And the very first thing for that is that you have to parse out the ID of the cert. So this is literally the first thing that you can do to this, like literally the first code path that you find, and that's what it does. So it's like a straight up easiest in the world, stack buffer overflow, where you control hundreds of bytes of data passed to PC, so, perfect, easy. The other thing that I found actually more interesting, the bug, so I mentioned, was in the client certificate manager. So this is also kind of nice. This is the point of this TrustZone is supposed to be that it makes the way you store your private certs on Android even more secure. So instead of it being on a file system and you only rely on SE Android or things like this to secure access to it, you can put all your certs into TrustZone, and then the keys never leave TrustZone. You just use it as an oracle, and then you can install some kind of authentication method for it, which can be password-based or trusted UI-based. The whole point is supposed to be that if you're a privileged user, then you can, with a password, you can log in, and then you can use your cert, and basically it will work as an oracle, which is lovely and everything, except when I looked at how this exactly worked, the way it worked is, remember that even though we're unprivileged, we can't talk to it. And so there's a command which opens a session, and this creates a random 64-bit session ID. And then when you have the session ID, you can do the login. For this, you would have to know the password. And when you logged in, they just flip a bit, saying this session is logged in. And after that, if you do any encrypt or decrypt comments with the right session ID, then that's it. Which, of course, means that if the actual owner of a cert tries to use the cert, and logs in, then I have a window where I can go ahead and do whatever with the keys, if I know the session IDs. Well, that sounds like they made a terrible mistake, but of course, 64-bit randomness, that's good. So there's no problem. So it's great, and sorry there was no bug, except for the fact that they logged the session ID into that SAC log that I mentioned, which is word accessible. So pretty much, it's basically the only thing literally that secures these certificate private keys is logged into a publicly accessible log. And even if, just to mention that even if you would be an application or process that for some reason maybe SE Android doesn't let you read that, of course, the way the logging works is all the TrustZone use the same buffer area for this for these in practice. So seeing the previous ability that we gained for getting code execution inside the TrustZone, like the EC-COM TrustZone, we can go ahead and read that out anyway. So basically, you can steal the session IDs, and then you can steal all the private keys that are stored in the super secure TrustZone. And, there was zero memory corruption. And, well, how much time do we have left? Because I think technically zero. Okay, 1 minute. So then let me just very quickly explain this as well. So to look beyond the TrustZone, I looked at this Tima driver, which does a million things, and among them, this is the thing that implements the driver part of the periodic kernel monitoring. And what that means is that Android can ask the TrustZone periodically to go and do hashes of the Linux kernel pages, code and data pages, and verify it against the golden copy. This is supposed to be so that you cannot batch code or whatever. But the problem here is that what this also meant is that there's basically a feature that the driver exposes to TrustZone that lets you essentially read the Android kernel. Well, you can only hash it and then get back the hash values, but the problem was that there actually is a TrustZone for this. There's a Tima PKM TrustZone which talks to this Tima PKM driver. However, the Tima driver doesn't verify that it's only this guy that talks to it. So if you're any of the other TrustZones, like the ESC-COM TrustZone, you can also talk to it, and you can just basically ask it to read Android kernel memory for you. And for example, you can use that easily to uncover the kernel ASLR slide. If you're not familiar with that, what Samsung does is there's always a fixed physical address, which is all zeros except for one D word, which is the kernel slide. So you just have to do one hash of that, and then obviously it's a trivially quick brute force to get it back. So again, no memory corruption, but now we're reading the Android kernel from a TrustZone. And then, I guess we really don't have time for any of this, which is sad. But in any case, I guess one takeaway is that, even if it's sort of a black box and whatever, you can still reverse engineer it to a pretty comprehensive degree. And I'm really hoping that by sharing this, we'll be able to start seeing that, if more people work on TrustZone, they don't again start from scratch, which has been the case in the past. That this great research always comes out, but the research always starts with and I'm starting this from zero. The other part about the thing that I would mention is that altogether, even though things are isolated pretty well, especially because exploit mitigations are really nothing as good as there's no address space randomization, for example, are not as good as in Android. I would say that if you want to look at TrustZone as a way to elevate your privileges from absolutely zero, it's not really the best place to look. I mean, obviously, I was able to find this DLC server bypass and go from there. But I would say that the bugs like that are going to be more rare. But if you're looking at a scenario where you have already had some decent privileges, and this is important to note that many of the things that now Google is trying to sandbox, DRM server and things like this, they have privileges to talk to TrustZone. So if you're in a situation like that, then all of a sudden the attack surface really grows. And I would personally say that if I compared, these days the difficulty with getting a reliable exploit, let's say in the Linux kernel or on a Samsung phone, versus trying to go through some TrustLab and a driver, assuming that again that you can, I think it's a very good attack surface. So that's about it, and I hope if you have any questions, or especially about the stuff I didn't get to talk about, then come find me. Let's close it there, and then maybe we have some time for questions. So thank you for coming. Any questions?
Mientras preparamos lo de la última charla del día, prendemos las luces y hacemos la gran tradición de Federico. Levantamos la mano para que los que están en el fondo encuentren su lugar. Los que estén con asientos vacíos al lado, por favor. Gracias.
Okay, so what did it say? Can there be questions or?
No. Sorry. English only.
Okay. Apparently no questions. I'm sorry about that, guys.